Just checking if everybody is here. All right, it seems like there are a bunch of people here, so we'll get started in a minute. But before we do, I just wanted to introduce here and introduce us. So I was yeah. Hi, my name is Anshuman. I'm actually one of the founders here at Scalar and InterviewBit. And just a little bit of introduction into what we're doing. So we started Scalar and InterviewBit with the goal that we wanted to improve tech education. A little bit about my background. I started my career with Facebook in the Silicon Valley. I spent about 4 years there, was part of the team that actually built out Facebook messages. Guys, can you hear me? Just say yes if I'm audible, say no if I'm not audible. There's some people who are saying lag. All right. All right. It seems like some people can hear me. I'll get started again, and do let me know if there is any problem now. So I was a software engineer with Facebook when I began my career. I was part of the team that actually built Facebook messages, Facebook chat. Later on, a Facebook Messenger as well, and um, and I was involved in hiring a lot of people while at Facebook. One of the things that I realized is that there's so many of us in India, especially. हमारे पास बहुत लोगों के पास एक्सेस नहीं होता है तो अच्छे एजुकेशन का एंड लाइक आई हैड सीन माय ओन ब्रदर आल्सो स्ट्रगल देयर so wanted to come back and make a difference there. Me and my other co-founder Abhimanyu, we both moved back to India and started InterviewBit. And InterviewBit was, I'm sorry, it seems like the video is lagging. All right, anyway, I'll keep continuing if it all it seems like the voice is clear, it's just that the video has a little bit of lag, so please bear with me there. um, Maybe just let me try reconnecting. Give me 1 second. Give me 1 second.
All right, guys, can you hear me? I guess Anshuman will be reconnecting his video in a second and then we'll resume, okay? Anshuman, are you there?
Yes, I'm here. Can you go live?
Oh, yes, we are live.
All right. Yes. Okay, cool. So I'll very quickly introduce. So basically, we started InterviewBit with the mission of helping people people with learning coding. We started InterviewBit with that, and later on we did Scalar, also with a very similar initiative. How can we make more difference to people's lives? And it is in the same spirit that we are starting a series of free classes for people to learn coding. And the reason why we're doing so is because we believe coding and software engineering is something that will become more and more important as we go forward. Most of the jobs are being automated now. That means it is very important for all of us to know coding. Some can be good coders, some can be not so good coders, but knowing coding is super important. So it is with that vision that we said how can we make more difference, and that's why we've started this series of free classes. And you'll see a lot of good things happening here as we go forward. Not a lot of new features, a lot of new prizes, etc., etc. But since there's an internet issue from my end, so I'm going to cut my introduction short and hand it over to Prag. Prag, if you're here, please take over, introduce yourself, and then
Yes.
like, the floor is over to you.
Right. So, guys, are you able to hear me? Yes. Are you able to hear me? Cool. So, thank you, Anshuman. I'll take it from here and let us begin the class then. Right. Thank you so much. All right. So, hello, guys. My name is Pragya. I am a senior software engineer here at Scalar Academy. And let us dive right into the class. So we are going to be covering the basics of time complexity, asymptotic notation, and things like that today. All right, perfect. Cool. So first of all, before we begin, I want to wish everyone a very happy Independence Day. So I hope you all celebrated it, but safely in your own houses, right? Cool. So then let us begin with the class. Before we begin with the class, there are a couple of announcements that I would like to make. So we are going to do this class every day. All right. So every day at the same time from 6:30 p.m. to 7:30 p.m. we are going to have this YouTube live class. So please make sure that you mark your calendars. All right. We are going to do this in sort of a curriculum, in a proper curriculum way. So we are going to introduce time complexity today. Tomorrow we will be discussing about arrays and maths and so on and so forth. Right. So please make sure that you do not miss any single class because this will be like a course. Okay. Apart from that, we will also be giving you some assignments and some questions to solve. All right. So you get complete hands-on practice. All right. And this will continue for a very, very long time. So you will have this completely free, completely open online course that will be with you on YouTube every single day. Okay. Cool. So, I mean, after this video, you will also be able to go in the link of the video description. So, in the video description of YouTube, you will be able to see a discussion link and also the test set, right? So, we'll have some practice problems for you. So, the link for both of them will be in the video description. Okay, cool. So, which language? So, we will not be following a particular programming language over here. We will be mixing and matching most of the languages. Will we be getting a certificate for this? Not really, Akash. This course is completely open for everyone to take. So there will not be any certificate for this particular course. Okay. Cool. So is what I'm writing clear? Is this iPad screen clear to everyone? Is this visible? Will the recording be available? So the recording will be present always on YouTube. Right, so we are currently live on YouTube. So as soon as the stream ends, the video will automatically be available on YouTube. All right. Can we do the session on Zoom? Raj, we will look into that or later on. Yes, the videos will be uploaded to YouTube after that. Cool. So let us begin. Let us begin with a very simple scenario. Okay, so we have some scenario over here. The scenario looks like this. So let us take two people. So we have Ruchika in the chat and we have Akshat, right? So let us say that we have two people, Ruchika and Akshat, right? Now both of these people, Ruchika and Akshat, they created an algorithm for sorting, right? They created a sorting algorithm, and the challenge is that whoever's sorting algorithm runs faster, that person will win the contest, okay? And they will get some prize. Is that fine? Cool. Now, Ruchika and Akshat both test their program, and here are the results. Right. So Ruchika uses an algorithm called Ruchika sort. Ruchika sort, and we benchmark that algorithm, and it turns out that Ruchika sort takes 5 seconds to run. Okay. On the other hand, Akshat uses his own algorithm. So Akshat's algorithm, and Akshat's algorithm takes around 10 seconds or 20 seconds to run. Okay, cool. So who do you think wins in this particular contest? Who do you think has a better algorithm, has a faster algorithm? Is Ruchika's sort better or is Akshit's sort better? Well, it seems like Ruchika is the winner over here, right? It seems like Ruchika is the winner over here because her algorithm runs in only 5 seconds, whereas Akshit's algorithm takes 20 seconds. But hey, but Akshit says, wait. This is not fair, right? Ruchika was running her algorithm on a top of the line MacBook Pro, right? Ruchika was running her algorithm on a top of the line MacBook Pro, whereas Akshit was running his algorithm on his mobile phone, right? So it is obvious that hey, Ruchika's algorithm will run a little faster because she was running it on a better computer. So we said, okay, that's fair enough. Let us try to run both the algorithms on the same MacBook Pro. Okay. So Ruchika's algorithm takes 5 seconds once again, but Akshit's algorithm now takes only 1 second. Yes. So when we ran Akshit's algorithm on the MacBook Pro, it took only 1 second. Now, who is the winner? Who is the winner now? Is it Ruchika or is it Akshit? Well, now that we have standardized the underlying hardware, now it makes sense that Akshit is the winner, right? But we are not done yet. We were trying to declare Akshit as the winner, but Ruchika said once again that hey, let's just wait a second. We are trying to run this algorithm to sort 1,000 different items. Okay, we were sorting 1,000 different items using this algorithm. Ruchika said that instead of sorting 1,000 elements, if you instead sorted 1 million elements, right? If you instead sorted 1 million items, then Ruchika claims that her algorithm will run faster. Right? Now that sounds a little weird. That I mean, for 1,000 items, Ruchika's algorithm is slower, but for 1 million items, Ruchika's algorithm will be faster. But that totally happens, right? Depending on the complexity of that algorithm, that can totally happen. So I hope that you can understand from this particular scenario that analyzing the time complexities of different algorithms is not that simple, right? We cannot simply measure the time. We have to do a lot more careful analysis. Is that clear? So we have to do some sort of a careful analysis. All right. So here are the things that we need. So we want a way that takes the following into account. So number one, it standardizes the underlying hardware. Right? So we want to make sure that whenever we are testing two algorithms, they are running kind of on the same hardware. Or basically, what we want to say is running on a faster computer should not change who the winner is. Does that make sense? Yes? So just because some algorithm is running on a slow computer, some algorithm is running on a faster computer, that should not change who the winner is. Right? The second requirement would be programming style. It would be programming style. It could be that Ruchika is a very, very good coder and she knows how to perform that coding, how to optimize her program a lot. Right? Whereas it could be that Akshit is kind of a beginner and Akshit does not know how to optimize the cache maybe and how to write the program so that it is very, very efficient. Right? So we have to make sure that while comparing algorithms, we do not compare the programming styles. We do not compare the underlying hardware. And finally, we have to make sure that we are testing with large enough data, large enough input, right? So just because for a smaller set of inputs, Ruchika's algorithm ran slower, that does not mean that Ruchika's algorithm is in fact slower. Right? We have to test it for a very, very large input. So we are trying to come up with a way of analyzing algorithms that satisfies all these three criteria. Is that clear? And the way we do that is by talking about, instead of talking about the time it took to execute, we instead talk about the rate of growth of the algorithm, right? Or we talk about the time complexity of the algorithm. Is that clear, guys? Yes, perfect. So let us see how we model this in a mathematical manner. Okay. So let us take a few more examples before we move on to the mathematical definition. Right. Let us suppose that we have two functions. Okay. We have two functions. One of the functions is, let us suppose, log x. Log x. So what does the graph of log x look like? Can someone tell me what the graph of log x looks like? So the graph of log x looks something like this, right? Log of 0 is not defined. Log of 1 is 0. And as x increases, the value of log x increases monotonically, right? But it increases slowly. So this is the graph of log x. Let us look at another function. Let us look at, say, x equals to 10. Right? So what will the graph of x equals to 10 look like? What will the graph of x equals to 10 look like? Well, it will look like something like this. It will look something like this. Yes. So what do you think? Which function is larger? Which function looks larger? Is x equal to 10 larger than log x? Does that make sense? Well, on the graph, we can see that it is certainly above log x, but that is not perfectly right. Okay. So the thing is that as we keep on increasing the value of x, right? As we keep on increasing the value of x, there will be a certain point. There will be a certain point which will be, let's say, x is around, let's say, 2000. After which this log x line, the graph of log x will eventually cross the graph of x equals to 10. Does that make sense? Oh, sorry, not x equals to 10, y equals to 10. My bad. Y equals to 10. Y equals to 10. Right? Does that make sense, guys? So eventually what will happen is the graph of y equals to 10, this graph will become less than the graph of y equals to log x. Yes? Now, why does that happen? Why does that happen? That happens because we are talking about the rate of growth of two functions, right? This particular function, y equals to 10, this function does not grow at all. 10 is a constant, right? Is everyone aware what a constant is? Y equals to 10, in that 10 is a constant. Whereas when y equals to log x, this log x, this is not a constant. It will grow with increasing values of x. It will continue growing and growing, right? So when we are comparing the time complexities of different algorithms, we do not want to compare the runtime, the time it took for one particular instance. We want to compare how the function grows. All right. Let us look at one more example. Let us suppose that we have this graph once again. So we have log x that looks like this. And we have y equals to x by 100. Right? So y equals to x by 100 will look something like this. Y equals to x by 100. Right? So now which one do you think is the faster algorithm? Which algorithm do you think is better? Well, currently in this particular part, till this particular point, y equals to x by 100. This was larger than log x, right? However, from this point onwards, log x was actually greater than y equals to x by 100. Yes. So should we say that log x is slower? Log x takes more time. Should we say that? Well, not necessarily. If we keep on increasing the value of x, what we will encounter is that log x grows much more slowly, whereas the graph of y equals to x by 100, that eventually crosses the line of log x. All right. So eventually for very large x, we will always find that x by 100 will be larger than log x. Now the challenge here is that we have to choose sufficiently large x, right? We can't talk about small values. We have to choose a large enough value of x. Does that make sense? Right? Yes, cool. Now let us ask a couple more questions. If I take this x equals to 100 graphs, right? And if I compare it with log x, instead of comparing this x equals to 100 or y equals to x by 100 graph, if I multiply this with some particular constant, right? If I say that instead of comparing x by 100 versus log x, What if I compare 1000 times x by 100, right? Times x by 100 versus log x. Is that going to change which algorithm is faster or which algorithm is slow? Yes or no? By multiplying a particular function by some amount, should that change if an algorithm is faster or slow? Well, that should not change the winner of the algorithms, right? Why should that not change? Because this is like running it. This is like running the program on faster hardware, right? Multiplying this value x by 100 by a constant amount 1000, this is like running that same program on a faster hardware. So we already wanted a method. We want a method in which change in hardware does not really affect our winner, right? Irrespective of which hardware we run the program on, the winner remains the same. So this should not affect the value. Similarly, if instead of multiplying with a constant, if I add a constant, right? If I add a constant, this also should not change the winner of my contest, right? This should not change the ordering of my algorithms. Is that clear? And the way we talk about this mathematically, is called the asymptotic notation, right? Now you will come across a lot of different asymptotic notations. The most common being the big O notation, designated by something like O of Fn, right? Then there is the omega notation. This is designated by this symbol, and we have the theta notation, which is this, right? So we will be talking about in details about what each of these different notations and each of these different methods mean. Is that clear? Any doubts till now? Repeat the hardware part. Okay. So basically, what I'm saying is, let us say that we have two algorithms, A and B, right? Let's say that A took T seconds to complete, while B took M seconds to complete, right? Now, if I measure which algorithm is better based on the time it took to complete, that measurement is not a very good measurement. Why? Because it could be the case that I could be running A on faster hardware and B on slower hardware, right? Or it could be the case that a genius programmer coded A while a newbie programmer coded B, right? So we want a way that abstracts out these differences. We want a way that does not care about the underlying hardware. We want a way that does not care about the underlying implementation, right? Which is why we want a method that makes sure that the rate of growth of algorithms is compared rather than the time it took. All right? Okay. So now let us look at the definitions of these asymptotic notations. Cool. So first of all, let's look at big O, right? Big O notation. This is denoted as O of Fn. All right. So let us first write the mathematical definition of this, and then I will explain what this means. So big O of Fn is actually defined as a set of functions that grow at most as fast as f of n. Does that make sense? So we are saying that any function whatsoever, if that function grows at most as fast as f of n, then that function is part of big O of fn, right? Mathematically, so we will talk about the rate of growth. Mathematically, we will denote this as big O of fn is the set of all functions gn, right? Big O of fn is the set of all the functions gn such that the function grows at most as fast as fn. How do we denote this? How do we denote this mathematically? How do we denote the rate of growth mathematically? All right. So let us look at how do we denote the rate of growth mathematically. So first of all, we want to make sure that the multiplicative constants, the underlying hardware does not really affect, right? The underlying hardware does not really affect it. So we are going to say that, okay, gn must be less than or equal to fn, but we can allow for some multiplicative constant. We can allow you to multiply any constant c over here. All right. So we are saying that for any constant c, for some constant c, right, there exists a constant c, such that this holds, right? That's the first thing. We do not want multiplicative factors to affect our rate of growth. Secondly, we want to make sure that we are measuring for a large enough input, right? We do not care about small inputs. So we will put another constraint over here. We will say that this will hold true. This will hold true for all n which are greater than some value of n, right? Which are greater than some base value. Now we are not defining what this base value is. We are saying that it should be just greater than some particular value. After this value, no matter what value of n you choose, as long as you have some constant and your value is greater than n0, then gn will remain less than or equal to fn. Does that make sense? Yes, this is how we define grows at most as fast as fn. Basically, let us suppose that this function is fn, right? And let us suppose that this function is gn. Now we want to check if gn is a part of big O of fn, right? So we are going to say that, all right, let us first not talk about small values of n, right? Let us not talk about small values of n. Let us define a very big value n0. Let us define a very big value n0, and we will only be considering all the values of n that are greater than n0. We will only be talking about this part. In this part, it could be the case that gn is above fn or gn is below fn. However, if I'm allowed to multiply fn with a constant c, which is greater than 0, and I can make sure that by doing that, fn is always above gn, right? If by multiplying fn by a constant c, I can make fn always above gn, then I can say that fn grows at least as fast as gn, or I can say that gn is in big O of fn. Does that make sense? Yes. So once again, big O of fn is the set of all functions that grow at most as fast as fn, right? Mathematically, it is defined as the set of all functions gn such that there exists a constant c which is greater than 0, and for all n is greater than n naught, right? For whenever these constraints are satisfied, then gn must be less than or equal to c times f of n. This is how we mathematically represent this statement. All right, these two statements are completely equivalent. Yes, these lectures will be available on YouTube. All right, cool. Now let me take some questions. Let me take some simple questions. So let us suppose that we have fn equals to n plus 6. All right, this is one function, fn equals to n plus 6. Let us try to list down what big O of fn is. Right. So can someone try to guess what big O of fn is going to be? Can someone try to give me an answer over here? Sumit asks, do we need to know this part to calculate the complexities of in a program? Yes, Sumit. Understanding the meaning of big O notation and understanding the meaning of asymptotic notations, asymptotic complexities is very important. Right? If you do not really understand that part, then you might end up at incorrect answers and you will not understand why your answer is incorrect. Okay? Cool. So what all functions do you think are part of big O of fn? Well, of course, y equals to n is definitely a part, right? So basically f of n equals to n. It is slower than n plus 6. Does that make sense? Well, what about fn equals to n by 100? Is that also a part of big O of fn? Yes, that is a part of big O of fn. What about fn equals to 100n plus 600? Well, it seems that 100n plus 600 is greater than n plus 6. Right? It seems that 100n plus 600 is greater than n plus 6. But please remember that we have this constant that we are allowed to use. Right? We are allowed to multiply fn with a constant. So this is also allowed because we can simply multiply fn. We can multiply fn with a constant like 1000. right? And then 100 plus 600, 100n plus 600 will be less than 1000n plus 6000, right? So this is definitely a part. Well, there are a lot of other functions that are also part of big O of Fn. For example, Fn equals to, or let me call these GNs, right? Let me call these GNs. Gn equals to log of n. Log of n also grows slower than n plus 6. So this is also part of big O of Fn, right? Similarly, under root of n, right? Similarly, log n to the power 5. All these functions are part of big O of Fn. In fact, this set is infinitely large. In fact, this set is infinitely large, right? There are infinitely many functions that are part of this set. Is that clear? Yes? Perfect. Okay. So now that we understand what the big O complexity means, let us quickly look at the order in which we know that let's look at some rules of big O complexity. Okay. So let us compare the following things. So we have a constant, right? We have a constant function. This is represented as Fn equals to some constant c. All right. On the other hand, we can have some sort of a logarithm, right? This is represented as Fn equals to log of n, right? With some base b, right? With some base b. Okay. We could have a square root, right? This would look like Fn equals to under root of n. We could have more. We could have something like linear. Right? This will look like Fn equals to n. We can have quadratic, right? Fn equals to n square plus 10 maybe, right? And so on and so forth, right? So we can have cubic. We can have any polynomial with any degree, right? Then on a high level, we can even have exponential. So this will look like Fn equals to 2 to the power n, right? Fn equals to 2 to the power n, or Fn equals to 1.5 to the power n. Whenever the base is greater than 1, then it is exponential, right? Cool. Then is exponential the highest complexity that we can talk about? Certainly not. We can keep going, right? So we can define something like factorial maybe. We can define factorial. So this would be Fn equals to n factorial maybe, right? We could have nested exponentials. So we could have Fn equals to n to the power n, right? We can continue infinitely. We can continue infinity both in this direction and in this direction, right? Can something be slower than a constant though? So not in this direction, but over here. Can something be slower than a constant? No, right? Because a constant literally does not grow. A constant does not grow at all. So the constant is the least amount of growth that is possible, right? But there are functions that can lie between this and this. Does that make sense? So this is in increasing order. Is that clear, guys? This is an increasing order of the complexity. Constant grows the slowest. It grows the slowest. So if a function grows slower, what does it mean? Is the algorithm faster or slower? So if there's an algorithm that takes this much time, and we are saying this function grows very, very slowly, right? In fact, this function does not grow at all. Grows slowly. So what can I say about the algorithm? Is the algorithm fast or is the algorithm slow? Right? So when the complexity grows slowly, the algorithm is fast. Algo is fast, right? Whereas when the complexity grows quickly, the algorithm is slow. All right. So we want our algorithm to have a complexity that grows very, very slowly. Does that make sense? So an algorithm that runs in constant time, that algorithm is the fastest algorithm. An algorithm that runs in logarithm time, that algorithm is pretty fast, right? An algorithm that runs in factorial time, that algorithm is extremely, extremely slow. Is that clear? Yes? Cool. So let me ask you a couple of questions. Of course, you will find many more questions. So I will be giving you a couple of questions over here, but if you want to practice more questions, you will find the link in the video description. right? So in the YouTube video description, you can go and there will be a link to a set of questions over there. Just go over there and try those questions out. Right? So, I mean, I hope that you understand this distinction between active learning and passive learning. Right? If you just watch a lecture like a movie, right? If you just listen to that lecture, you do not take notes and you do not practice, then you will be getting some of the benefit, but you won't be getting all of the benefit. Right? On the other hand, when you actually take notes, when you actually write your notes yourself, and once the lecture is over, when you actually practice the problems, that is going to help you out a lot. All right. Yes, Ashish, whatever I'm writing over here, you will be getting that. So once this lecture is over, this entire PDF will be uploaded in the link in the video description as well. Shahrukh says there's no link. Vikas also says that there's no link. Okay, so I'll just get that checked. All right. So just give me a second, guys. Let me just quickly get that checked. So by the time this lecture ends, that link will be available over there. Okay, so do not worry about that. That link will be available by the time the lecture ends. Okay, cool. So this was a lot of theoretical stuff, right? This was a lot of theoretical stuff about what asymptotic notations are. Now let us actually look at some code. Let us actually look at some code and try to see if you can figure out what the asymptotic complexity of that code is. All right. Now, figuring out the asymptotic complexity of a particular piece of code can be very, very difficult, right? So for example, if you have a recursive function, or if you have a complex data structure, right? Then analyzing the time complexity of that piece of code can become a little more difficult. So we will not be covering this today, not today, all right? However, we will be taking a class. We will have a complete set of classes on recursion. Right? We will have a set of classes on recursion. We will have a set of classes on different data structures as well. So when we talk about recursion, we will talk about analyzing the time complexity of recursion as well in that particular session. All right. Today we are only going to look at very simple pieces of code and trying to analyze the complexities of those pieces of code. Is that clear? Cool. So let us begin. Let us begin. So suppose I have written a program that looks something like this. I declare a variable int x equals to 10, right? And then I do something with, maybe I do print x, right? Let us suppose this is my piece of code. How much time do you think this code takes? How much time does this code take? How much time do you think this code takes? Well, whenever we have trivial operations like this, whenever we have trivial or simple operations, then usually those operations take a constant amount of time, right? A constant amount of time. So this particular operation, this is a declaration, and there is also an initialization, right? So what will happen is the computer will allocate some memory. The computer will populate that memory with the value 10, and the computer will move a lot of stuff in and out of the CPU, in and out of the RAM, in and out of the cache, and things like that. Right? Similarly, when we are calling the print function, what will happen is the computer will load the address of x. Right? It will load the address of x. It will load the address of this print function. Right? And then it will invoke this print function with this particular address. Right? Whatever this print function does, it will also do that. So we are assuming over here that all these operations take a constant time each, right? So this one takes O1 time, this one takes O1 time. All right. So overall, this entire program takes a constant amount of time. Is that clear? Very simple, very easy thing, right? But this is not that simple, right? We have to be a little more careful. For example, let us say that I have, instead of x equals to 10, I have a vector of int. Right? So vector of int is just a list of it. So if you are coming from a programming language like Python, so this is in C++. In Python, you would just have x equals to list of something, right? In Java, maybe you will have x equals to array list, right? Array list of integers and so on, right? Let us suppose that we have a vector of int. So we are saying x equals to vector of int, and it has, let's say, a size of 1000 elements. Right, 1000 elements. Right? Or let us say that it has a size of n. It has a size of n. What if I try to do something like this? Print x. How much time do you think this print x will take now? How much time do you think this print x will take now? Well, earlier we said that print x was going to take a constant amount of time, right? But now it will not take a constant amount of time, because in order to print a large array, it will have to go through that entire array, right? It will have to go through that entire array. So whenever we are talking about very simple data structures, whenever we are talking about the basic data types, right, like integers, like floats, then the operations on them will be constant amount of time. But when we have larger data structures, for example, when we have vectors or when we have hash maps, right, then operations on them can take more time. So for example, in this case, the print function will take order of n time. It will be linear. Does that make sense? So we have to be careful over here. We have to be careful before we simply say that, okay, this is constant time. We have to be a little more careful. Okay. Now let us move on to some more, some control flow structures. All right. Suppose that we have code that looks like this. If condition, right? And if this is the condition, then we do some work over here. That takes O of fn time. Else, we do some work over here that takes O of gn time, right? So basically, we are saying that if this condition is true, we will go into this part, we'll go into this block, and the time complexity of this block is order of fn, right? Whereas if this condition is not true, we'll go into this block, and the time complexity of this block is order of gn. So if this is the case, then what is the time complexity of this overall piece of code? What is the time complexity of this overall piece of code? Yes. Well, the time complexity of this overall piece of code is, it is the maximum out of fn comma gn, right? So you will basically say that this is order of max of fn comma gn. Is that clear? Yes. Right? Cool. Alternatively, you could have also said that this is order of fn plus gn, right? Even though depending on this condition, you will only go into one of these blocks, right? It is not the case that you're going into both these blocks. However, asymptotically, this and this, they are exactly the same. Why are they the same? Why are they the same? Can somebody tell me that? Because these are related by a constant factor. Right? These are related by a constant factor. If I just multiply this value by 2 times, right? If I just multiply this value by 2 times, then this value, 2 times this maximum value, will become greater than fn plus gn, right? Which is why it doesn't really matter which one we say. Is that clear? Cool. Now let us move on to loops, for example. All right. So we just covered if-else statements. They are a part of control flow. Let us move on to loops. So let us suppose that we have a for loop, something like this: I equals to 0, I less than n, I plus plus, right? And in this loop, let us say we are doing print I. Yes. So whenever we are talking about loops, we have to look at the time complexity in different parts. Okay. So first of all, we will say, what is the time complexity of this inside block? What is the time complexity of this inside block? What is the time complexity of this inside block? Well, this is constant, right? Printing a particular value, it takes just one step, right? So this inside block is constant. Then we will see, okay, how many times are we going to run this inside block? So this inside block, although it takes a constant amount of time, it is not going to be run once, right? We are going to run this again and again. How many times are we going to run this? Well, how many times this loop will run, right? So that is how much this loop goes from 0 all the way till n minus 1. So that is n times. Yes, that is n times. So it turns out that the complexity of this entire program is n times order of 1. Right? N times order of 1, which is nothing but order of n. Is that clear? Yes? Cool. Let us look at nested loops. So nested loops are very similar. So suppose that we have for I goes from 0, I less than n, I plus plus, right? And we have suppose j as well. So we have a nested loop inside this for j goes from 0, j less than let's say n, j plus plus, right? And over here we do print suppose I plus j, right? Suppose this is our code. Then once again, we will look at the innermost block. We will look at the innermost block. And we will say, okay, what is the time complexity of this block? Right? What is the time complexity of this block? Well, the time complexity of this block is just order of 1 because we are printing an integer. Right? We are printing a single integer. So the time complexity is just order of 1. Then we will ask ourselves, okay, how many times are we going to run this block? How many times are we going to run this block? Well, the answer is not so simple, right? The answer is not so simple because both these loops are going to run this block again and again. So let us break it down further. Let us say that, okay, let us not worry about the outside loop. Let us not worry about the outside loop. Let us look at this piece of code. Right? Let us look at this piece of code. What is the time complexity of this piece of code? Well, we just saw it earlier, right? The time complexity of this piece of code is order of n. This is order of n. Why? It is order of n because we are running this O1 operation n times. Right? This loop will run n times. So this time complexity is order of n. Then we will say, okay, now this blue block here takes order of n time, and we are going to run this blue block n times. Right? So what is the overall time complexity? It is n times big O of n, which is big O of n square. Is that clear? Yes? Right? So I hope that you now understand how to calculate the time complexities of nested loops. All right? Now we have to be a little more careful once again. In this particular loop, why was this loop taking order of n time? So if we have a loop that looks like this for I equals to 0, I less than n, I plus plus, we say that this loop ran n times. Does everyone agree that this loop ran n times? Yes. What about if we had a loop that looks something like this? For I equals to 0, I less than n, I plus equals to 2. Right? Instead of incrementing by 1, what if we incremented by 2? Or what if we incremented by 200? Now the loop will not run n times, right? Now how many times will the loop run? If this is the case, then how many times will the loop run? It will run n by 200 times. Yes, n by 200 times. Well, let us look at the time complexity in that case. Let us say that inside this, we were doing O1 work. Right? Inside both these things, we were doing O1 work. So the time complexity of the previous block was n times order of 1, which was order of n. The time complexity of this block is what? It is n by 200 times order of 1, which is what? Which is order of n by 200. Well, order of n by 200 is actually the same as order of n. Is that clear? The order of n by 200, the big O of n by 200 is actually the same as big O of n. Right? Because as we said, in the big O time complexity, in the asymptotic notations, we kind of ignore the constant multiplicative factors. Right? Any constant multiplicative or additive factors can be ignored. Is that clear? Yes? Cool. So no, these are separate loops, guys. These are separate loops. These are two different pieces of code. We are saying what happens when we do I plus plus, whereas compared to that, what happens when we do I plus equals to 200. All right. This loop will run n times. This loop will run n by 200 times. These are different pieces of code, right? They are not nested loops. Okay, these are not nested loops. Yes. So yes, it is true. It is true that this particular loop runs 200 times less. Right? This loop runs only n by 200 times, whereas this loop runs n times. But the time complexity, the asymptotic time complexity of both the loops is the same. Is that clear? Yes. Okay, so Saurav has a question over here. Saurav says that, okay, when we did this if-else condition thing, when we did this if else condition thing, you told us the following. You told us that big O of Fn plus Gn is the same as big O of max of Fn comma Gn. Right? This is what I said. Let us try to prove why this is the case. Okay, let us try to prove why this is the case. All right. So let us go to the definition of big O once again. Okay, let us go to the definition of big O once again. Let us look at this particular part over here. Okay, let us look at this particular part. So I am going to prove that for large enough n, right? When the value of n0 is large enough, and for some constant c, I'm going to prove the following: Fn plus Gn is less than or equal to c times max of Fn comma Gn, right? And this will be for all n greater than n naught. Yes. If I can prove this, then what will that mean? That will mean that order of that will mean that Fn plus Gn is actually an element of big of max of Fn comma Gn. Is that clear? Yes. Does that make sense? Cool. So let us see if this is true or not. Well, let us fix n naught. Let us say n naught equals to 0. Okay, let us say that n naught equals to 0. So we are having a very small value of n naught, that does not matter. Let us now choose a value of c. Let us say that c equals to 2. Okay, let us say that c equals to 2. Well, if c equals to 2, then does this equation hold? Fn plus Gn is less than equal to 2 times max of Fn comma Gn. Is this equation true? Yes, this is true. Why is this true? Well, we don't really know what is larger between Fn and Gn, but let us suppose that Fn is larger. Right? Let us suppose that Fn is larger. So what will this be? This will be 2 times Fn minus some delta value, because Gn is smaller than Fn. Whereas on the right hand side, we have 2 times the maximum of Fn and Gn will be Fn itself. So that will be 2 times f of n. So we see that yes, this equation in fact holds, right? Which is why we can say that Fn plus Gn is an element of big O of max of Fn comma Gn, right? Similarly, we can do this the other way around as well. We can also prove that max of Fn comma Gn, this is in fact less than or equal to some C2 times Fn plus Gn for some large enough value of n, right? So we can prove this the other way around as well. So that will mean that this does not just go one way, right? This is true, but also this is true. Max of Fn comma Gn is an element of big O of Fn plus Gn, right? So this is also true. And if we put these both together, we see that hey, irrespective of what function I choose, I can say that this function grows faster than this function, right? If I am telling you that x is less than y, x is less than equal to y, and I also tell you that y is less than equal to x, what does that mean? If I have both these equations, what does that really mean? It means that x is just the same as y. Yes? Is that clear? So over here, we can say that f of n plus g of n is the same as max of Fn comma Gn, right? But this is not correct, right? This is not correct. We have to be careful. We do not mean equals to over here, right? We do not mean equals to over here. Clearly, these two functions are not equal. We mean the order of growth, right? We mean the order of growth is equal, right? Now this equation is correct. Is that clear? Yes? Perfect. Cool. So let us look at one more for loop, for example. So suppose we have a for loop that looks something like this. So we have for I goes from 0, I less than n, I multiplication equals to 2, right? Then print I. How much time do you think this particular loop will take? How much time do you think this particular loop will take? Well, let us look at what happens in this loop, right? What happens in this loop? So initially, so let us start with I equals to 1. In fact, let us start with I equals to 1, right? So initially I equals to 1, right? Then we will print 1. Then what will happen? I will be multiplied by 2, so I becomes 2. So we will print 2. After that, I becomes 4. Then I becomes 8. Then I becomes 16, and so on and so forth. Right? So I is doubling each and every time. Right? I is doubling each and every time. So if I has to reach n, right? How many steps will it take to reach n? That is the question. If I keeps doubling each and every time, how many steps will it take to reach n? That is the question. Will it take n steps? Will it take under root of n steps? Will it take n by 2 steps? Will it take log n steps? What do you think is the answer? Well, this is the answer, right? It will actually take log of n base 2 steps. Right? It will take log of n base 2 steps. Is everyone familiar with this? Right? This is via the definition of log n. Right? I hope that everyone is familiar with this. If you are not super comfortable with this, not a problem. Just join the discussion. So there will be a link for the discussion after this video is over. Right? In the chat, there will be a link for the discussion. Just join over there, and I can explain that to you in much more detail. Why this is going to take log n steps. All right? Cool. So this particular loop, this particular piece of code, this takes order of 1 time, and we are going to do that log n times. So the complexity of this code is overall going to be order of log of n. Is that clear? Yes? Perfect. Let us look at another example maybe. Let us say that we have for I equals to, let us say 1, right? And we can say that, okay, let us have j is less than n, I plus plus. Okay, so please note over here, let's not make it j. Let us say that this is k. Let us say that this is k. So we are going from I equals to 1, we are incrementing I, and we are checking the condition with respect to k. And inside the loop, we will write k equals to k plus I. Is that clear? Is this program clear? So initially k equals to 0. Initially k equals to 0, and we are going from k equals to 0 all the way till k equals to n, and this is the program. So let us see what will happen. Let us see what will happen. So how much time is this inner part going to take? What is the time complexity of this inner part? Well, very simple once again. This is just order of 1 time. Right? This just takes order of 1 time. But how many times are we going to execute this? Right? How many times is this code going to run? Is this loop going to run? Let us try to analyze that. Right? So initially k is 0 and I is 1. Right? Initially k is 0 and I is 1. So when we do this, k will become 1. Right? When we do this, k will become 1. Okay. Then what happens in the next step? What happens in the next step? We go to this thing, right? I plus plus. So I becomes 2 now. I becomes 2 now, right? So when I becomes 2, what will k become? What will k become? K will become, so k was earlier 1 plus 2, which will now be 3. Right? So k equals to 3. Yes? Does that make sense? Let us look at the next step. Let us look at the next step. So now I equals to 3. K will become 1 plus 2 plus 3. Right? 1 plus 2 plus 3, which will be actually equal to 6. Right? So we will print k equals to 6, and so on and so forth. So how much time do you think it will take for k to reach n? Right? How many steps will it take? How many steps will it take? So after the first step, k was 1. After the second step, k was 3. After the third step, k was 6. After the fourth step, k will be 10, and so on and so forth. So after how many steps? After how many steps will k be greater than or equal to n? That is the question. Right? What is the delta here? The delta here keeps changing. Right? The delta here keeps changing. Initially it was 1, then it became 2, then it became 3, then it became 4, and so on. It will keep on increasing. Right? So that is the question. So can someone tell me the answer? Well, we will have to do some mathematics over here. Right? We will have to do some mathematics over here. So basically what is happening with k is At the ith step, the value of k is equal to 1 plus 2 plus 3 plus all the way till I. Do you guys agree? At the ith step, this is the value of k. Yes, because that is what we are doing, right? We are incrementing the value of I and we are adding it to k every time. So at the ith step, this is the value of k. All right. So let us try to solve this. So do you guys know this? Do you guys know the formula for this? What is the value of 1 plus 2 plus 3 all the way till n? Right. You can also write this as the summation for I equals to 1 till n of I. Right. This is the sum of first and natural numbers. Can someone tell me the formula for this very quickly? Can someone tell me the formula? This is simply the same as n into n plus 1 by 2. Right? This is also known as the nth triangular number. This is also the same as n plus 1 choose 2. Right? You can represent the same thing in multiple ways in mathematics. You can say it like this, 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 and you can say it like this. All right, so many different ways. Okay, so now that we know this formula, what we are basically saying is that at ith step, k equals to 1 plus 2 plus all the way till I, which is nothing but I times I plus 1 by 2. Right? That is what we are saying. At the ith step, k will have this value. Right? Now our question is, at what step will k be greater than or equal to n? Right? That is the question. Is this clear? So we have an equation to solve, right? So we are basically saying if at the ith step k is this, then at what step will k be greater than or equal to n? So let us simply place the value, right? We want I times I plus 1 by 2 to be greater than or equal to n. Yes? I into I plus 1 by 2 is greater than or equal to n. Right? So basically I into I plus 1 is greater than or equal to 2n. Right? And if we solve this, if we make it in terms of I, right? If we make it in terms of I, so remember what we have to find. We have to find the value of I because we want which step, how many steps does it take. So it will turn out that I will come out to be of the form square root of n. Right? It won't be exactly square root of n. It will have some particular value over there, but the effective will be that I will be order of square root of n. Is that clear? Yes. Yes, how do you actually solve for I from this? How do you actually solve for I from this? So you can make it into a quadratic equation, right? So you can say I square plus I is greater than or equal to 2n. Then you can say I square plus I minus 2n is greater than or equal to 0. Then you can solve it with the minus, so minus b plus minus root over of b square minus 4ac by 2a. Right? You can put the value of b, the value of a, and the value of c to find the final value. And it will turn out that I will be of some form of root n. So I is the order of root n. So what we are essentially saying is that the loop will run order of root n times. Yes, the loop will run order of root n times. And how much work are we doing in every single iteration? In every single iteration, we are doing a constant amount of work. Right? In every single iteration, we are doing a constant amount of work. So overall time complexity will be order of root n times order of 1, which is nothing but order of root n. All right. So the time complexity of this particular loop will be order of root n. Okay, cool. So I guess we will end the lecture for this today. So today was very simple concepts, the very basics of time complexity, very simple loops, very simple if else statements, right? We are going to cover a lot of things in a lot of depth, right? So when we will have the class on recursion, we will tell you how to understand, how to analyze the time complexity of recursion. When we talk about sorting, we will consider the time complexity of sorting. When we talk about graphs and trees, we will talk about the time complexity analysis for graphs and trees. All right. So do not worry about that. Today was a very simple introductory class. We will have this class each and every day, right? So every day from 6:30 p.m. to 7:30 p.m. Right? So please mark your calendars and please do not miss a class. Because if you miss a class, then there will be a gap and you won't be able to understand what is coming next. Right? So if you miss a class, then you will have a gap. You will have a backlog that you will have to maintain. All right. Yes, I will be sharing this. I will be uploading this this notes that I have, and I will be putting it in the video description. Okay. Cool. Perfect. So guys, if you have any further questions, so you have two tasks, right? After this video is over, you have two tasks. So this is the YouTube video. Over here is the description, right? In this description, there will be two links. There will be two links. One link will be of the discussion, right? One link will be of the discussion. What you are supposed to do is you are supposed to go to that discussion link and you are supposed to join the chat over there. So in that chat, I will be available. In that chat, a lot of different instructors from Scalar Academy will be available. And in that chat, a lot of other people from YouTube will be available. Okay. So you will be able to talk about things. You will be able to ask questions and we will be able to answer you live. Okay. The other thing will be a test. Will be a practice set basically. Not a test, a practice set. Right. There will be a link for the practice set as well. So if you go there, you will find several questions on the stuff that we have discussed today. So on the time complexity of for loops and on the complexity analysis, you will find a lot of questions there. And please do practice those questions. Because if you don't practice the questions, you will forget the stuff. Right? Once you practice the questions, you will remember it forever. Okay. Ronak says, sir, nothing here. So Ronak, if you're not able to see anything in the video description, it could just be that you need to reload the page. Okay, so once this video is over, just reload the page and you should be able to see that. All right. Cool. So guys, same time tomorrow, 6:30 to 7:30, and let us discuss something like arrays maybe tomorrow. All right. Cool. All right then, guys. Have a nice day. Bye-bye. Happy Independence Day once again. And let's see you tomorrow. All right.